Hi everyone, my name is Nehasree Uma Tadikonda and I'm a student at BSc Honours Data Science and Artificial Intelligence program at IIT Guwahati. This video represents my third project submission, loan approval and default risk prediction with explainable AI. Quickly, here's what I'll cover. The problem I worked on, the tools and the dataset, the two-stage modeling pipeline, loan approval and then default risk, how I made the predictions explainable, on what I learned along the way. Coming to the problem statement, every lender makes two decisions for each applicant. First, should this loan be approved at all? Second, and only if it was approved, how likely is this loan to default? I found this interesting because most projects treat this as two separate unrelated classification problems, but they are not separate. A loan that was never approved was never disbursed, so it can't have a default outcome. I wanted to build a pipeline that actually respects that connection instead of training a default model on data that couldn't exist yet. That constraint became the core design decision of the whole project. My objectives were to explore the data with SQL, build classification models for approval, build both a classical machine learning model and a deep learning model for default risk, evaluate all of them properly, and explain the predictions with SHAP and LIME. For tools, I used Python with pandas and NumPy for data handling, SQLite for SQL exploration, scikit-learn for approval models, XGBoost and TensorFlow and Keras for default risk models, imbalanced learn for handling class imbalance with SMOT, and SHAP and LIME for explainability. My dataset is a single unified table that represents the full loan lifecycle application, approval decision, and for approved loans, default outcome. I built it to match the schema of two public reference datasets since I couldn't find one dataset that spans the whole lifecycle with consistent applicant records. This dataset has 1,000 applicants, out of which 68% are approved, and among those approved loans, 24% are default. The most important design decision here, the default status field is only populated for approved loans. For rejected applications, it left empty. Because that loan was never disbursed, so it never had a chance to default. This is a real data leakage trap in credit risk modeling, and I wanted my pipeline to handle it correctly rather than just avoid it by accident. Here's the full pipeline. Every applicant goes through cleaning and feature engineering, then the approval model. Only the applicants who are approved move into the second half. Their own cleaning and feature engineering pass, the default risk models, and finally, explainability. Let's start with stage 1, loan approval. In the first notebook, I loaded the data into SQLite and ran a few SQL queries. For example, approval rate by credit history, which jumps from around 9% to about 8%, depending on whether the applicant meets the credit history guidelines. That single feature turned out to be the strongest signal in the whole dataset, which lines up with real underwriting practice. In the second notebook, I trained a logistic regression and a random forest after balancing the classes with smooth. Logistic regression etched out random forest on ROC AUC curve A 0.852 versus 0.830, while random forest has a higher recall, meaning it missed fewer applicants who should have been approved. Credit history, loan to income ratio, and total income were the three strongest predictors. Now for stage 2, default risk. Before anything else, Notebook 3 filters the dataset down to only the loans that were actually approved. That's the data leakage safeguard I mentioned earlier. I loaded the data into SQLite and ran a few queries. This stage was noticeably harder. Both my classical ML model and my deep learning model landed around 0.71 to 0.72 ROC AUC curve compared to the 0.85 for approval. That makes sense. Whether someone meets basic eligibility criteria is fairly deterministic, but whether they'll actually repay a loan over years depends on things that haven't actually happened yet. The gradient boosted model had a higher precision, while the neural network had a higher recall, catching more true defaults but with more false alarms. In practice, which one you'd pick depends on whether your business cares more about missing risky loans or rejecting good ones. Interest rate, negative amortization status, and loan to value ratio came out as the leading risk drivers. This is the part of the project I think matters the most. In lending, applicants and regulators are often entitled to know why a decision was made. So, a model that performs well but can't explain itself isn't actually reliable. I used SHAP to get both a global view, which features matter the most across all applicants, and a local view, explaining one specific applicant's prediction. I also used LIME as a second, independent local explanation method, and I wrote a small function that turns SHAP values into plain language explanations. Something like this applicant's risk was increased by a high loan to value ratio and decreased by strong credit score. The features SHAP ranked highest are credit score, loan to value ratio, and interest rate. These are exactly what a credit risk analyst would expect, which gave me real confidence, and the model was learning genuine signal, not noise. On the key takeaways slide, a few things I'd like to highlight. Approval is genuinely easier problem than default risk, which showed up clearly in the EOC gap. The ML versus deep learning choice is a real trade-off, not a clear winner. So I'd pick based on different business priorities. The explainability results validated that the whole pipeline was learning sensible relationships. And honestly, the architecture decision filtering to approved loans before modeling default mattered as much as any specific model I trained. To be honest about my limitations, my dataset is synthetic, built to match two public schemas rather than one real life cycle dataset, and is fairly small at 1,000 applicants. I also haven't done a fairness audit across attributes like gender or region yet, which I'd want to do before testing this in any real setting. For the future work, I would like to validate this on real data, tune hyperparameters more systematically, run that fairness audit, and possibly extend default prediction into a time to default formulation instead of a single yes or no outcome. That's my project. Thank you for watching. The full code and notebooks are on my GitHub, linked on the screen and in the report. Thank you.